Welcome to the second lecture video in our Class 6 time series of lecture videos. At the end of our first lecture video, we decided to stop right about the point where we asked, what about the cyclopentadienyl cation? Because we had just gone through a lengthy discussion of how the cyclopentadienyl anion is aromatic and how it can form sandwich complexes with transition metals by, conveniently having its molecular orbitals in the right phase and geometry to overlap with d orbitals. Well, our cyclopentadienyl cation is cyclic, it's planar, it's fully conjugated. So those are the three criteria we need to meet before we can decide whether it's aromatic or anti-aromatic. How many pi electrons are in that cyclic, planar, fully conjugated cyclopentadienyl cation? Well, there are 4 pi electrons, because there are 2 electrons in each of these double bonds, and so 2 times 2 is 4. There are no electrons in this empty p orbital that has the formal positive charge in this Lewis structure that's drawn for it. So that makes it a 4n pi system, which means it's anti-aromatic. That means it's highly reactive and unstable, and it's actually difficult to generate. For that reason, if we looked at its molecular orbital diagram, again, we'd do a Frost diagram, and we would see, oh, it behaves like a diradical, right? Because its degenerate Psi2 and Psi3 molecular orbitals each only have 1 electron, because as we fill electrons into this molecular orbital system, we put 2 in the lowest energy molecular orbital Psi1, and then when we go to the next level in energy, we find that we have 2 degenerate molecular orbitals, which means they each get 1 electron before we start pairing electrons. But we're already out by the time we reach 4 electrons. So 4 little molecule is a diradical, which makes it reactive and unstable. This is a subject which every year it seems like my students have trouble digesting. Neutral heteroatom analogs of cyclopentadienyl anion can also be aromatic. This is known as pyrrole. We've got this 5-membered ring, right? Heteroatom means we've got a different atom than carbon. It happens to be nitrogen. Oh, look, it has a lone pair of electrons. Well, that lone pair of electrons is in a p-like orbital, right? The hybridization around our nitrogen atom is sp2-like. It likes to be in a p-like orbital because guess what? Once it is, we have a nice stable aromatic system, and it's neutral, right? We've got 2 pi bonds. That's a total of 4 electrons, plus the nitrogen atom lone pair, 2 electrons. That's 6 electrons, right? That's a 4n plus 2 aromatic system. We know there's a lot of stability associated with these aromatic systems. How about furan? Well, we've got same 5-membered ring. Now we've got an oxygen. Oh, 2 lone pairs of electrons. Well, one of these lone pairs of electrons is in a p-like orbital. The other lone pair of the electrons is in an sp2-like hybrid. And only the pair of electrons that's in the p-like orbital can really overlap effectively with the other p orbitals of the pi system in our cyclic planar fully conjugated molecule, right? This pair of electrons is basically in the same plane as the other atoms of the ring, right? And so these sp2 hybrid-like orbitals can't really overlap with the p orbitals that are in the pi system of this aromatic molecule. So that's why only one of the lone pairs of electrons counts to determining how many electrons are in the pi system of our cyclic planar fully conjugated molecule, and the other pair of electrons, it does not count. It is perpendicular to the pi system, so there's no overlap. So again, we've got 2 pi bonds, 4 electrons, and 1 lone pair that's counted in a p-like orbital of 2 electrons, so that's 6 electrons. That's a 4n plus 2 system. It's aromatic. There are other molecules that students might have trouble with. Maybe we'll discuss some during the actual class time. But for now, we'll continue on with another interesting example. here we go. Let's consider cyclooctatetraene. Discovered, published around 1911, so more than 100 years ago. What are some observations? It's cyclic. It's more stable than cyclobutadiene, right? It's comparable in stability to an alkene. There are 4 pi bonds, so we would think, 8 electrons. What's going on, right? Shouldn't this be like a 4n, anti-aromatic type molecule? But then we have to ask, is it planar, right? Because we have to meet that criteria, right? In order to actually achieve full conjugation, that is overlap of every p orbital at every adjacent carbon. So cyclooctatetraene is non-aromatic. That's because it's not planar. We can't classify it as aromatic or anti-aromatic. And because it's not planar, that really destroys the conjugation. What do I mean? Well, the actual, nice low energy configuration of the cyclooctatetraene is sort of boat-shaped if we take a look at it, which really means there's minimal resonance overlap, even though I still maintain that resonance is a lie. What I really mean is there's minimal overlap of the p orbital lobes, right, on these adjacent carbons. So they act more like isolated alkenes. The 4 pi bonds are isolated, no overlap. Hence, each pi bond acts like an alkene. We can see that our double bonded carbons are 1.34 angstroms, and our single bonded carbons are very characteristic of carbons that possess single bonds, about 1.48 angstroms. Got a 126-degree bond angle there. That's nice. Take-home message, non-planar means it can neither be aromatic or anti-aromatic. Well, geez, we're only 7 minutes into this video. Hopefully I haven't put you all to sleep yet. We might as well, discuss other cyclic pi systems. This is 18-annuline. That's a much easier way of naming that molecule than its actual, 1, 3, 5, 7, 9, 11, 13, 15, 17 cyclooctadecanoniene. Yikes. There's something kind of interesting about this molecule, right? It's got 18 carbons, hence 18-annuline, right? How many, it's cyclic, it's planar, it's fully conjugated. There are 9 pi bonds for 18 electrons. That fits the 4n plus 2 formula where n equals 4, right? It's an aromatic compound. It's something that can be synthesized and isolated. And what's kind of interesting is it has 2 different types of hydrogens, right? There are hydrogens that point outside of the ring, and then there are these hydrogens that point internal to the ring. We'll venture back to discuss 18-annuline when we hit, NMR on some of these molecules. So last sort of parting shot, gift for this lecture is the cyclopropylium cation. This is generated by deprotonating, not deprotonating, by pulling a hydride off of cyclopropene. So what do we have? We've got a cyclic, planar, fully conjugated molecule, right? There are 2 electrons, which means it's aromatic, right? 4n plus 2, n equals 0. You could make a Frost diagram for that, and you could even, speculate as to what the 3 molecular orbitals look like by adding, appropriate nodes, shading of your p orbitals. Good luck. And I'll see you in the next video.